Okay, welcome back. We are thinking about Hubble's law, the relationship that he discovered where the distance a galaxy is from us is directly proportional to its recessional velocity, how fast it's moving away from us. Great, so let's think about an equation, the next slide, an equation that will describe the line on the graph on the previous page. So let's just go ahead and do this. What is the equation of a straight line? Well, if you remember back to your high school or, I don't know, middle school math classes, the equation of a straight line is y equals mx plus b. So I'm going to share my whiteboard with you again. So the generic equation of a straight line, y equals mx plus b, where recall, y is your y variable, x is your x variable. This is m is the slope, and b is your y-intercept. Great. So we have a straight line, so it must be that this is the case. So let's go back to that line and think about what y and x are and what the slope and intercept have to be. Here we go. Here's our slide back again. What is y? Well, y is velocity and d is distance. So y is velocity and d is distance. I'm going to write those down. You're not seeing them, but I want you to see what the y-intercept of this particular graph is. It looks like the y-intercept is 0. In other words, at 0, distance of 0, the velocity is 0. This all seems to come right back down to the origin. And so we go back to our whiteboard. So the y variable is velocity, the x variable is distance, the y-intercept we think is 0, and the only thing we have to worry about now is the slope here. We'll still call it m for now. But basically, Hubble's law, that relationship boils down to v equals some constant times d. And we call this constant h sub 0, or the Hubble constant, after Edwin Hubble himself. So this, v equals h naught times d, is the Hubble law. It describes, for a galaxy at a given distance, what its velocity is expected to be from this law, and at a given velocity, what we expect the distance to be. This particular galaxy, let's go back to PowerPoint. Great. So we've written an equation that describes the line on that page now. The slope of the graph is known as the Hubble constant. I just told you that. The Hubble constant. What are the units on the Hubble constant? The Hubble constant has some very strange units. Let's go back and think about this. The units of slope are slope is rise over run. So the units of slope have to be the units of rise divided by the units of run. In this particular case, those units are kilometers per second, which is the y-axis, per megaparsec. So that's weird. Let's go back here. The slope the whole slope on the graph is known as the Hubble constant. The units are kilometers per second per megaparsec. And that leads us to this equation, which I basically already written down. V is the recessional velocity or radial velocity. In this case, they're all moving away from us. H naught is the Hubble constant, and D is the distance of the galaxy. And H naught has these weird units because we want D to be a distance that's relevant for distant galaxies like megaparsecs, and we want V to be a unit that's appropriate for measuring radial velocities, which is kilometers per second. And so H naught has to come from those units. And so you get these weird kilometers per second per megaparsec for the actual Hubble constant. And that gives us a number that's, kind of nice between 0 and 100. I should say this is one of those parameters that hasn't been all that well known and is still kind of debated today. When I first took my astronomy class, when I took my first astronomy class many years ago in the mid-90s, we didn't know what this was. There was a camp that thought this was about 50. There was a camp that thought this was about 100. There was a factor of 2 uncertainty in what this Hubble constant is. It's much better today, but there's still 72 is not all that definite. It's most people would probably now say 70 plus or minus a couple for the Hubble constant. It's still some uncertainty in all of these distance and measurements. Okay, so let's use this formula. We can now use this formula to get relative distances and radial velocities if we know one or the other. So let's say a galaxy is found to have a distance of 50 kiloparsecs, 50 times 5 times 10 to the 7 parsecs. It's actually 50 megaparsecs. What is the expected radial velocity? Well, let's do it. Now we'll notes and come back to the whiteboard. And go ahead and do it. So our V equals H naught times D. Let's set, we know that D is 5 times 10 to the 7 parsecs. We know that H naught is about 72 kilometers per second per megaparsec. And we want to know what V is. Well, all you have to do is multiply those two together, but you're going to want this megaparsec to go away, and so you're going to need this to be in megaparsecs. Well, a mega is 10 to the 6, so we could multiply this by, we know that there is 1 megaparsec for every 10 to the 6 parsecs. Parsecs go away. 5 times 10 to the 7 divided by 10 to the 6 is actually 50. It's 5 times 10 to the 1, which is 50 megaparsecs. So V is equal to 72 kilometers per second per megaparsec times 50 megaparsecs. The megaparsecs go away. Got the 50, and this number comes out to be about 3,600 kilometers per second. So the star, the galaxy has a distance, a known distance of 50 megaparsecs. We expect it to have a radial velocity of about 3,600 kilometers per second. Here's one for you, although I guess I'm going to do it anyway because we have no top hat anymore. A galaxy is found to have a recessional velocity of 50,000 kilometers per second. What is its expected distance? The cool thing is once we know what the Hubble constant is, we can use a galaxy's velocity to determine the distance to it. And that's useful. I guess I'll go ahead and do this again. Oh, I didn't even show you the, here, let me show you the next slide real quick where I'm posing this question. There it is. A galaxy is found to have a recessional velocity of 50,000 kilometers per second. What is its expected distance? Let's go back to the whiteboard. So V equals H naught times D. In this case, we want distance and have velocity. So we need to divide both sides by D and divide both sides by V also. The V's go away over here, the D's go away over here. We get, sorry, I didn't want to do that at all. Let me start that over. V equals H naught D. We want to solve for D. All we need to do is divide both sides by H naught. That's a much better thing to do. H naughts go away, and we get D equals V over H naught. Our velocity in this case is 50,000 kilometers per second. And our Hubble constant is 72 kilometers per second per megaparsec. The kilometers per second go away. 50,000 divided by 72 is 694. And the units are megaparsecs, which is in the denominator of the denominator. So it comes back up to the numerator, 694 megaparsecs. 694 million parsecs. 6.94 times 10 to the 8 parsecs away. That's a lot of meters. The universe is a big place. Okay. How long has light taken to reach us from the particular galaxy that we're talking about? Again, this is a simple math equation. Let's go ahead and write it down. Do some erasing here. Okay, so this is the 694 megaparsecs, and we're interested now in how long it has taken that light to get to us from that galaxy. Well, we need to know our distance. We need to know basically how far away this is in light years, because if we can figure out how far away it is in light years, that will tell us how many years it's been since that light, how many years it took for that light to get to us. So if distance is 694 megaparsecs, that's, again, a mega is a million, so that's 694 times 10 to the 6 parsecs. Or, if you like, you can move the decimal over 2 and add 2 to the exponent. 6.94 times 10 to the 8 parsecs, doesn't really matter. You also need to know how many light years there are in a parsec, which you can look up. 1 parsec is 3.26 light years. So we can just do the unit conversion. We need light years on top and parsecs on the bottom. 1 parsec is 3.26 light years. So just have to multiply this number by 3.26, the parsecs go away, and we end up with light years. And the number you get is something like 2.3 or 2.26 times 10 to the 9 light years. 2.26 billion, because 10 to the 9 is a billion light years away, which means it has taken, it will take light, the light that we're getting from this galaxy now left that galaxy 2.26 billion years ago. That's the useful thing about light years. That's a, can't read that very well. Let me rewrite this. 2.26 billion years. And that's a significant fraction of the age of the universe, right? The sun's only, this is only about half the age of the sun. So this is a long time. This is one of the ways we can chart how galactic evolution works. We can actually see what galaxies were like in the past just by looking further away in space. Okay, I think I'm going to end there for the day. We have certainly covered everything on the first exam. In fact, the third exam. In fact, the material for the third exam does not include the Hubble constant or the expansion of the universe. So that will be on the final. We will do another, well, really only 3 classes after this. So we're winding up very quickly. But I hope you are all safe and healthy, and good luck on the exam this Thursday. Bye-bye.